Hello, can you hear me? Clear? Okay, so yeah, so we will gonna study about the remaining part of the optimization today. Okay, so so maybe next week we have to take some quick midterm exam. That's why some of the contents today will be a part of the midterm exam. Okay, so we will gonna quickly walk through the optimization part, and we're gonna walk through the reactant optimization later. So some of the we did up to here. So we will gonna study about the convex and concave functions from now on. Okay, so we're gonna go to this one. Okay, you see the slide, right? So we're gonna start right now. Okay, from today, we're gonna talk about what is the convex and what is the concave. Okay, so when the graph look like below, then we are saying that this curve is concave, convex. Then what is the formal definition of the convex function? So when you look at this one, when you have this kinds of the equation, then you have convex. Okay, you have the function f. This is the function f. Okay, and you have function f. You have c constant value, and then you have c here, and you have 1 minus c here, and you have any kinds of the x values for f. Okay, and then you multiply with c, you multiply with 1 minus c, and sum to each other, and then you are doing the same thing for only pure x, not the result of the function f, and then you put the result into the function f and compare. Okay, and then if the left-hand side is smaller or equals, and then you are saying that the function is convex. But this kind of the definition is too formal, and then it's not intuitive. Then you have to look at the below. Okay, then so look at this function, and then look at this illustration, and then let's understand what is the convex with this illustration. Okay, when you look at this illustration and you have this curve, you put arbitrary 2 points over here. Okay, and then you put A, you pick D. Okay, and you made a line with A and D, and then you pick any kinds of the point on top of the line A and D, and then suppose that C is the point which is on top of the line AD, and then C is always on top of the B. B is the value on top of the function f, and then we are saying that the function is convex. Let me repeat again. Okay, suppose that you have function f. Okay, you pick 2 points on top of the f, A and D. Okay, arbitrary 2 points on top of the f, and then make a linear line AD. Okay, over here, and here between x prime and x2 prime, pick any kinds of the point between here, and then you pick C. In the same vertical line, you pick the point which is the intersection with the function f, then that is the B. And then f should be always higher or equals to B. Then the function f is convex. Then the convex always look like a curve. Then we are saying that that is the convex function. When your function is convex, then it means that your function is always look like curve. Okay, then you are saying that the convex function guarantees optimal solution in polynomial time. Okay, that is the intuitive understanding for the convex function. Let me repeat one more time. Okay, so suppose that you have function f, pick 2 points A and D. In this case, you can pick another point. Okay, and then make a linear line here, AD here, and pick any kinds of point on top of AD. Here, the number is C. okay? The point is C. And then make a vertical line, that is B. And then the vertical line should meet the function f, and the point is B. And then the C should be always higher or equals to B. And then you are saying that the function f is convex, okay? And then you can easily imagine that the function look like a cup. Then the function is convex, okay? That is an easy understanding, intuitive understanding of a convex function. And this one is mathematical understanding of the convex function, okay? And then you have to keep in mind that when your given function is convex, it means that when your given function look like a curve, and then your optimal, your minimum point value can be obtained in a polynomial time. It means that this value, B is the minimum value of this function f. This B point can be obtained in a polynomial time. That is the given theory, okay? B can be obtained. B is the minimum of the given function f. B can be obtained in a polynomial time. That is the convex optimization, okay? So concave is the opposite definition of the convex, okay? Concave look like this one, okay? So suppose that you have function f. You pick the 2 points on top of the f, and then you can make a linear line. You can pick any point on top of the linear line. Here, the point is the B, okay? And then you make a vertical line. You should find the point where the line meet the function. Then the point is C. And then the C should be always higher and equals to B. And then your given function is concave. That is the opposite definition of the convex. That is called concave function. Then you can intuitively imagine that your concave function is always look like a hat. Then your maximum value of your given concave function can be obtained in a polynomial time, because there is the negative value of the convex, okay? That is very easy theory in optimization, okay? So here, consider nonlinear programming here. Consider nonlinear programming and assume that there is the maximization problem, okay? Suppose that you are talking about the concave set. Concave set means that your function look like a hat. Here, in this case, you are talking about the minimization, and then your given function is convex. That means that your function look like a cup, okay? And then your function is concave, and then your local maximum value here is always optimal. So you don't need to look at every single space. You don't need to look at entire space here. Just to find local maximum, and this value is the entire global maximum. That is trivial, right? Because it looks like a hat. When you find the maximum one, that is the maximum in entire space because it looks like a hat. In a similar way, when you find the minimum value in a convex function, there is no way to have another solution which is lower than this one. That's why this is the local minimum. However, this is the global optimal, global minimum value. That's why any local minimum value here is the optimal solution to this minimization problem, okay? This is talking about that, and this is very trivial, okay? And then here, suppose that you are talking about this one, okay? And suppose that you are doing the second order derivation for this function, okay? In a convex set, okay? This is convex function because it looks like a cup. And then your second order derivation exists for all x in convex set. And let's look at this one, okay? Then let's make an example. So this one is y is x squared, okay? For this one, okay? Theorem 3.7, okay? Then please do the first order derivation. Then it becomes 2x, right? Then please do one more time for the derivation. Then you have to calculate the second order derivation. It becomes 2, right? This is the result of the second order derivation. Then this is the positive value. This is always positive value when the given function is concave. That's why the second order derivation is always positive or zero, right? In a similar way or in an opposite way, suppose that your second order derivation exists and that is the convex set. And then you are talking about the concave function. Then it looks like this one. Then you imagine the function just like this one, right? Then please do the first order derivation. Then it becomes minus 2x. Please do the one more time. Then minus 2. Then it becomes negative value. That's why it becomes negative value. Okay. So you look this one. Is negative value or 0? Then it becomes concave function, right? This should be the concave as well. This is typo, okay? So you have to keep in mind this one, okay? When you do the second order derivation, you will gonna see you have some chances to see the constant value. If the value is positive, then you are handling some convex function. When you look at the negative value, then it means that you are handling the concave function. It means that you are talking, so for the first case, when you do the second order derivation, you see the positive value, then it means that you are talking about the convex function, then you are dealing with the minimization problem. As you can see in previous slide, in the second theorem, when you do the second order derivation, then you have the negative value, then you are dealing with the concave function, then you are dealing with the maximization problem. Then it means that when you do the second order derivation 2 times, when you have the negative value, then you are for the maximization problem. You know, above side, when you do the second order derivation 2 times, when you do the derivation 2 times, that is the positive value, then you are dealing with the minimization problem, okay? So now we are talking about the Hessian, okay? Hessian is very, very important for us, okay? So Hessian is the n by n matrix whose ij entry is just like that. It means that for the given matrix, you are doing the partial derivation with j component at first, and then you are doing the partial derivation with I later. So you are doing the partial derivation with j first and I later, okay? Then let's do this one with one example, okay? So let's look at this example. So find the Hessian of this function. So you have 2 variables, x sub 1, x sub 2. That's why you have 4 possible combinations for the Hessian. In Hessian, you have 2 derivations, right? You have 2 types of the variable, x1 and x2. That's why in Hessian, you are doing the derivation with the x1 2 times. You are doing the derivation with the x2 and x1. You are doing the derivation with the x1 at first, and then x2. You are doing the partial derivation with the x2 2 times, right? So you have 4 different types of the Hessian computation. I'm sorry? Okay, so let's do the partial derivation for this one with the x of 1. Then this becomes a 3x squared and plus, and when you do the partial derivation with the x sub 1, this becomes 2x sub 2, and this will be considered as the constant term. This will disappear. You only have this one, and then this one, when you do the partial derivation with the x sub 1 at first, you will get this result and this one, right? And you are doing the partial derivation with the x sub 1 again, and then this becomes 6x sub 1, and this will consider as the constant value. This will disappear. You only have this one, right? Then you put this one in 1, 1 position because you are doing the partial derivation with 1, 1, okay? And now you are doing the partial derivation with 2 at first. You are doing the partial derivation with 2 at first. So you are doing the partial derivation with 2 at first. So this one will be constant as the constant term. That's why this one will disappear. And this one will only have this one, 2x sub 1. That's why you only have this one. This one will be considered as 2x sub 2. That's why you have this one. Now you are doing the partial derivation with the x sub 1. That's why this one will disappear. appear because this one will be considered as a constant. You only have this one. That's why this one will disappear. You only have 2. That's why you have 2. This one is 1,2 position. This one is 1,2 position, right? So now for the next time, for the next, you have partial derivation with 1. That's why this one will be becomes 3x sub 1 to the 2. That's why you have this one. This one becomes 2x sub 2. You have this one. This one will be considered as a constant. That's why this one will disappear. That's why you only have this one. Okay. Now you are doing the partial derivation with x sub 2. That's why this one will disappear. You only have this one. Okay. That's why you only have 2. That's why this one becomes 2 because this one's position will be 2, 1. Lastly, in the position of the 2, 2, you are doing the partial derivation with x sub 2 times. So for the given function for this one, you are doing the partial derivation with x sub 2 for this one, and this one will disappear. This one will 2 multiplication x sub 1, and this one will be 2x sub 2, and then you are doing the partial derivation with x sub 2 again. That's why this one will be 2. That's why you have this result. This is the Hessian with this given function f. Okay, you have to remember how to calculate the Hessian. Then continuous function, you have to keep in mind that you have partial derivation with x sub 2 and x sub 1 later. This one x sub 1 first, x sub 2 later, and they are same to each other. You can swap. Okay, that's why they are same to each other. So they will be same to each other in all the cases in the end of this lecture slide. Okay. So you will have another concept that is called the principal minor. Okay, you have to remember this one as well in order to use the Hessian concept in the optimization. Okay, so here what is the principal minor? On I's principal minor of an n by n matrix is the determinant of I by I matrix obtained by deleting n minus I rows and the corresponding n minus I column of the matrix. Okay, so here for the given matrix for this one, finding the first principal minors and the second principal minors. So when you have 2 by 2 matrix, you can find the first principal minor and second principal minor. When you have 3 by 3 matrix, you can find the first principal minor, second principal minor, and third principal minor. When you have 4 by 4 matrix, you can find the first principal minor, second principal minor, third principal minor, and fourth principal minor, and so forth. Okay. When you have K by K matrix, you can have first principal minor, second principal minor, and so forth, K's principal minor. Okay. And here, the principal minor is the determinant. Okay. Okay. So here you have to find first principal minor. It means that as you can see here, this one will be the first principal minors. Okay, because based on this definition, when you look at this one, this is a 2 by 2 matrix, right? Because m becomes 2, m becomes 2, m becomes 2, right? M becomes 2. I can be 1 or I can be 2. Let's say I is 1. Okay, I is 1. I is 1. I can be 1, so I becomes 1. So 1 by 1 matrix, right? 1 by 1 matrix obtained by deleting first row and the corresponding first column. So you are deleting this one and this one. Now you only have this one. That's why you have this one, right? Or you are deleting this one or deleting this one. That's why you only have this one. That's why when you calculate first principal minor, then you are selecting the diagonal entries, right? That's why -2 and -4. You don't need to calculate anything. You just take anything in the diagonal entries, okay? Then what is the second principal minor? So in that case, as I told you before, you have to calculate the determinant, okay? So here, now, second principal minor, when you calculate the second principal minor, then I becomes 2. I becomes 2. N is 2. That's why 2 minus 2 and 0. then deleting 0 row, it means that you cannot delete anything. That's why you should not delete anything. That's why you have this matrix entirely. Then you have to calculate the determinant of this entire matrix. Then how you can calculate the determinant? You can calculate determinant in this way. That's why you have to multiply -2 and -4. That's why you have this one and minus, and then -1 and -1. That's why you have this one. That's why you have 7. That's why this is the second principal minor. Okay. So note, as I told you before, for the first principal minor, the first principal minors are just the diagonal entries of the matrix, right? Because when you have 2 by 2 matrix, and then for the first principal minors, deleting 2 minus 1. That's why you have first row and first column, right? So deleting these, just these entries, okay? So easy to understand, right? So let's look at the other parts. Let's look at the other chapters, okay? And then suppose that continuous second order partial derivative, then concave. So here, this theorem, you should remember this one, because this one shows why we have to understand why we have to know how to calculate the principal minors. So this theorem says that all principal minors of the Hessian matrix, all principal minors of the Hessians are non-negative, then the given function is convex. As I told you before, when you solve the optimization problem, you have to look at the objective function. When the function is convex or concave, you can guarantee the optimal solution. When your function is not convex or concave, you cannot solve the optimization problem. So when you have the optimization problem at first, you have to determine this one at first, right? That's why before starting, when you have the function, you have to convert this, you have to calculate the Hessian based on your given objective function or constraint. You have to calculate the Hessian at first. Based on the Hessian, you have to find all the principal minors. And then based on that, you have to check whether all the principal minors are non-negative or not. If all principal minors are non-negative, that's good. You don't need to worry about. The function is convex. You guarantee the optimal. That's it. Or all non-negative principal minors has the same sign as -1 to the k. It means that first principal minus signs are all negative. Second principal minus are all positive. Third principal minus are all negative. Fourth principal minus are all positive. Fifth principal minus are all negative. Sixth principal minus are all positive. Negative plus, and so forth. Then your given objective function should be concave. You have this theorem. This is very important. When your given objective functions Hessian satisfy this theorem, then your optimization guarantee optimal solution. Otherwise, your objective function cannot guarantee optimal solutions. Okay, that's why you have to do this one, right? Now, let's do this one in some examples, right? So suppose that you have this function, right? Then first of all, you have to find Hessian. Now, how you can get this Hessian? This one, you are doing the partial derivation with the x1 2 times. This one do the partial derivation with the x1 and then x2. This one is the partial derivation of this one, x2 at first and then x1. And then you have to do the partial derivation x2 2 times, then you can get the 2, right? Then you can get this Hessian matrix based on this function. You can easily do this one when you can do the simple calculus during your undergraduate courses, right? You do the partial derivation with the x1 2 times, then you get 2. When you do the partial derivation for this function, x1 and first and x2 later, then you get this one. When you do partial derivation x2 at first and x1 later, then you get this value. When you do partial derivation with the x2 2 times, then you can get this value, right? Then you have this Hessian, right? Based on this Hessian, then you have to calculate the first principal minors. Then what is the first principal minus? These diagonal entries, right? That's why now you can see that your first principal minus are second and second. That's why the diagonal entries are all positive values, are all non-negative values. That's why it satisfies the condition, right? Then now it's time to calculate the second principal minus, right? Then what is the second principal minor? That is the determinant of this given matrix. That's why you have to calculate this one and this one. That's why 4 minus 4, and then this is 0, which is non-negative. Then you can confirm that all the given principal minors are all non-negative. That's why you can confirm that the given function is convex. That's it. Very easy, right? Very easy. It's kind of high school calculus, right? So now let's confirm that this given function is concave, right? So for the given function, you have to do the partial derivation with the x1 2 times, then you can get this one. When you do the partial derivation with the x2 at first and then x1, then you can get this one. When you do the partial derivation with the x2 at first and x1 at first and x2 later, then you can get this one. When you do the partial derivation with the x2 2 times, then you can get this one, right? And then find the first principal minus, then you can take the diagonal entries, then -2 and -2. Then you can confirm that they are negative values. Then this is not convex, right? And let's look at the second principal minus. Then you have to find the determinant of this matrix, right? The determinant will be -2 multiplication -4, and minus and -1 multiplication -1, and -2 and -4 multiplication and minus and -1 and -1, and this becomes 7, and this becomes positive. And then now you confirm that your all first principal minus are all negative. Your second principal minus are all positive. I told you that your first principal minus are all negative. Your second principal minus are all positive. Then this is concave, right? That's why you prove this one, okay? Now let's go to the next example. Now show that this is not convex nor concave, nor. See, this is not anything. This is not anything. This is just nothing, right? This is just a random function. Let's prove that, right? So first of all, just to do the partial derivation with the x1 2 times, then you can get to do the partial derivation with the x1 at first and x2 later, and then you can get -3. You do the partial derivation with the x1 and x2 first and x1 later, then you can get -3. You do the partial derivation with the x2 2 times, then you find the 4, and you get this Hessian matrix, right? And then you have to find principal minus. For the first principal minus, you take the diagonal entries and 2 and 4. And 2 and 4, these are first principal minus. And then these are all positive values. Then it means that at least this is not concave. So this is not concave, okay? Because in concave, the first principal minus should be negative. But as you can see here, the first principal minus are all positive, right? And now it's time to calculate the second principal minus, right? For the calculation of the second principal minus, you have to do the calculation for the 2 multiplication 4 and -3 multiplication -3, and 2 multiplication 4 is 8 -3 multiplication -3 will be 9. This becomes minus, and this becomes minus. As I told you before, if this function should be, if this function is concave, all the principal minus should be non-negative. This is non-negative, this is non-negative, but however, this is negative. That's why this is not concave. So this is not convex. So this is not concave, nor this is not convex, okay? So this is just nothing, just a random function, okay? So you cannot guarantee optimal solution in a polynomial time. So now, so let's extend the dimension of the function, right? You have 3 variables, right? So now you have to make a Hessian. You did 3 by 3 because you have 3 variables, right? So you do the partial derivation with the x1 2 times, x3 first, and the x1 later, x3 first, x1 2 times, x3 first, x2 first, x1 later, x3 first, x1 later, x2 first, x1 later, x1 first, x2 first, x1 first, x1 later, x2 first, x2 later, x3 first, x2 later, x1 first, x3 later, x2 first, x3 later, x3 first, x3 later. Then you can get these values, right? Now, for the first order principal minus, I told you that you should take the diagonal entries. That's why you take the 2, 2, and 4, right? But I told, based on the definition of the first order principal minus, n is 3 because this is a 3 by 3 matrix in Hessian, and I is 1. That's why, but based on the definition of the principal minus in our previous ones, principal minus, if n is 3 and I is 1, then we have to delete 2 rows and 2 columns. That's why, based on the definition, I just want to make sure that you understand the principal minus clearly. That's why I want to calculate the first order principal minus based on the definition. That's why I'm doing this one. Okay, so based on the definition, n is 3, I is 1, because we are calculating the first order principal minus. That's why n minus I is 2. That's why we have to delete 2 rows and 2 columns. 2 rows, 2 columns, you only have 2. That's why this becomes 2. 2 and 3 are deleted. Okay, and now, and 1, 3 are deleted, and 2. That's why 2. Okay, and 1, 2 deleted, 1, 2 deleted, you have 4. That's why you have 4. Okay, and then eventually it is same with taking the diagonal entries. That's why 2 to 4. That's why 2 to 4. Now you observe that everything is positive. Okay, then at least you can confirm that this is not concave, because in concave, first order principal minus should be negative, but these are all positive. That's why this function is at least not concave. Okay, now let's look at the second order principal minus. Okay, in second order principal minus, n is 3, I is 1. Okay, that's why you have to I is 2. That's why you have to delete 3 minus 1, 3 minus 2, which is 1. So you have to delete 1 row and 1 column. So you have to delete this one and this one. That's why you have to this submatrix. Then you have to calculate the determinant of this one. Then 2 by determinant of 2, 2 minus 1 minus 1, this one. Or you have to delete these second ones. That's why 2 minus 1 minus 1 and 4. That's why this one, right? Or you have to delete the third one, this one and this one. That's why you only have this one. That's why you only have whatever, this one. Okay, then you have these 3 ones. So you have delete this one, then you take this one, then this becomes this one. Or you delete this one, then the result will be 2 minus 4. This one, this one. They are same, right? Then lastly, you delete this one and this one, then this becomes the last one, right? Then you calculate the determinant for individual submatrices. Then you calculate the determinant for individual submatrices, right? Then everything will be the positive, okay? And then lastly, for the third order principal minus, because here our Hessian is a third 3 by 3, that's why we can calculate up to third principal minus, right? Third order principal minus, right? That's why you have to calculate the determinant of this one. You know how to calculate this one, right? 2 multiplication determinant of this one minus this one multiplication determinant of this one and this one submatrix plus minus 1 multiplication this matrix's determinant, right? You remember your linear algebra class result, right? And then you can calculate this one. This is also positive. Then eventually you confirm that all the principal minus up to now 4, 2, 2, 7, 7, 3, 6, everything is all positive. That's why you can confirm that given 3-dimensional function in this example, is convex because all the principal minors are positive. So when you have 10-dimensional function, you cannot illustrate how it can be visualized. That, however, you can calculate whether this is convex, whether it looks like cup, whether it looks like a hat, based on this principal minor calculation. This is very important because when the function is convex or concave, then you can confirm that whether the given function's optimal value can be obtained or not immediately. If the given function is not convex nor not concave, then you cannot guarantee the optimal solution, right? That's very important. So that's the very important for us right now. So solving nonlinear problems with one variable, okay? So from now on, these are all straightforward and just high school mathematics. It's not that difficult at all. All the important things are already done with this one, okay? You don't need to worry about from now on too much, okay? To find the optimal solution, so how to solve the nonlinear programming problems for the maximization or minimization with a given interval A and B. So here you have the given interval A and B. So here you have B, you have A. So to find the optimal solution, we find all local maximum or minimum. Then the optimal solution is a local maximum having the largest value of the function. Then so in this case, when you want to find the maximum value, you have no solution. When you want to find the minimum value, you have no optimal solution. In this case, you have maximum value here, you have minimum value here. However, when you have no interval, then you cannot find the maximum or minimum in some cases, depending on the function characteristics. But that's why it's very important to consider the interval for the given function. It's very important to understand the characteristics of the given function, okay? And then there are three types of the point which can have the local maximum of the minimum. So this is very straightforward. So when you think about this one sitting here for just a few minutes, then you can understand everything, right? So points where that is between A and B, and then there is some value which is the 0 when it takes the derivation, result is 0, then there is some stationary point over there. That's straightforward, right? So if there is no stationary point when we have the first order derivation, then there is no stationary point. Then those intervals, endpoints will be the solutions. Okay, so endpoints A and B of the interval will be your values, desired values. Okay, so the case one, points where A and B. So you have interval A and B in the left-hand side and right-hand side, right? So suppose that this is the concave function, this is the convex function, and then when you take the second order derivation, then you can take the maximum value. This one first order derivation, you have 0. But when you take the second order derivation, this is the concave, that's why this will be the negative. This is the convex function, that's why when you take the second order derivation, this will be the positive, as we did before. And then when you take the first order derivation, that value will give you the minimum point. When you take the first order derivation, and then if that value is the 0, and the point will be the maximum value, okay? Local maximum, okay? And then this is between A and B, and suppose that the 0 point stationary point is existing between A and B, then you can find the maximum or minimum just like this way, okay? But however, in this case, this is kind of the this case can exist as well, okay? Here in this case, second order derivation is 0 exactly. In that case, this can happen. So in this case, first order derivation is 0, second order derivation is exact 0, then in that case, there is no exact minimum and maximum in the first order derivation point. In that case, we have to consider the A of function value or B of function value as minimum or maximum. You have to put A and B into this function and calculate the value, and you see whether there is a maximum or minimum. That's the way you can try. to get the maximum or minimum for the given function. So in this case, you have to think about the case where the first order derivation is not existing. So in that case, it means that your stationary point is not existing at all. So in that case, when your interval is x sub 1, x sub 2, there is no stationary point in a given interval. The right-hand side, the situation is almost the same. There is no stationary point between x1 and x2. So in that case, you put x1 and x2 into the function here, you put x sub 1, x sub 2 into the function as well, and then you compare the values, and you pick the maximum, you pick the minimum based on the function values. That will be the thing you can try to get the values, okay? Or if the function cannot be derivable, then the function is not continuous. Then this can be a discontinuous function. Then in that case, we cannot estimate at all. You cannot do anything with this one. You cannot estimate any kinds of behavior for this function. Then you have to use the heuristics. You cannot do anything with this function. You cannot do anything with this one. That's why you just discard this one. So if the function does not have derivative, then you cannot do anything, okay? All our basic assumption is that the given function is derivative. Then we can do some mathematical, we can try mathematical techniques for the given function. Otherwise, we cannot do anything, okay? So here, endpoint A and B of the interval. So here A and B here, A and B here, okay? Then this one is also you can consider. You can your minimum values, maximum values, minimum values, and maximum values. The values will be in the can be in the endpoints of the A and B. So that's also those can be the solutions for your given functions as well. Okay. So this one is also same. Okay. So very straightforward, right? So we just saw some all possible cases for the given functions. That's why it's very straightforward. That's why I talk very fast manner. Now we will go to the unconstrained optimization with the several variables. So it's very important for us. That's why we're gonna walk through this one for more details. Okay. So we wanna solve the problem. Maximization or minimization, or the minimization of this given function. And then this is unconstrained, which means that we have no constraints. And then we just have the one simple constraint, which just says that our solutions are just real numbers. And that's it. We just no specific constraint over here. We just have one function, convex or concave. If the function is convex or concave, then we can guarantee the optimal solution. That's it. However, there is no other constraints over here. That's it, okay? So then in this case, if the function look like any kind of shape in concave or convex, then when you want to find the maximum value or when you want to find the minimum value, your function should be on top of here or below here. That's why you have to find the maximum or minimum. Then that will be the flat. That's why that is called then that will be 0 when you do the partial derivation in all kinds of the variables. Then that will be the top or the bottom of the given function in all directions. So the function is n-dimensional. Then you have to do the partial derivation with n possible variables. And then all partial derivable values should be 0. The point will be the local extreme, okay? Then what's the stationary point? That is called the stationary point, right? Then the point is the n-dimensional point, and the point having the partial derivation with 0 for all possible n-dimensional x values, okay? So, so here, this is a Hessian. So let's look at the other examples here. Let's understand everything with this example. Then we can easily understand what's going on, okay? a monopolist producing a single product has two types of the customers. Okay, we have two types of the customers. We have Q sub 1 units are produced for customer 1. Then customer 1 is willing to pay a price of 7 minus 4 Q sub 1 dollars. If Q sub 2 units are produced for customer 2, and then the customer 2 is willing to pay a price of 150 minus 15 Q sub 2 dollars. Okay, then we have two variables, right? And we have this amount of unit, then they will pay this amount of the money. When we have this amount of the unit, then they will gonna pay this one. And this is our income, okay? And then for Q, which is larger than 0, the cost of the manufacturing Q is 10 plus 15 Q, and then Q will be the Q plus Q sub 1 plus Q sub 2, because you have entire Q among this given Q. Some of them will be the Q sub 1, some of them will be the Q sub 2. That's why summation will be the Q. That's why the manufacturing cost will be the Q unit will be the this amount of dollars. That's why Q will be the Q sub 1 plus Q sub 2. That's why this is the entire income. And then you have to take out the manufacturing cost. Then eventually, you can calculate the net income, right? That's why you have to do the minus of the 100 plus 15Q. That's why you have to minus 100 minus 15Q, and Q is Q1 plus Q2. That's why you have 15Q1 minus 15Q2. So you are taking out the manufacturing cost here, right? Then what's this? This is your net income. You are having the earning money. You are incoming minus manufacturing cost. Now your function F, your own profit, your net income, right? Now you want to maximize your net income. You want to maximize your profit, okay? So this is your function. You want to maximize this one, right? And you have two different type of the variables here. Then how we can do that, okay? Then, as I told you before, we have to find the stationary point, right? Then you are doing the partial derivation for the first variable. You have to do the partial derivation for the second variable, right? That's why you have to do the partial derivation for the first one. You have to do the partial derivation for the second one. So partial derivation with the first one. That's why with this function, you have to do the partial derivation with the Q sub 1. That's why this will disappear. Only this one will be considered. That's why this will be considered, and this should be 0, right? And this will be the partial derivation. This will be the partial derivation result with the Q sub 2, and this will be 0 as well. Then you can calculate what is the Q1. You can calculate what is the Q2, and then you can see that what is the stationary point, right? Next, we have to find the Hessian matrix for the given function. Then how we can do that? It's simple. You already know how you can do that, right? You are doing the partial derivation with the Q sub 1 2 times. You have to do the partial derivation with the Q sub 2 at first, and then Q sub 1. You have to do the partial derivation with the Q sub 1 at first and Q sub 2 at later. You have to do the partial derivation with the Q sub 2 2 times, and then you can make the matrix that is your Hessian matrix, right? So this is your Hessian matrix. Now you have to calculate the principal minus, and then this your principal minus -8 minus 30, and then you have to calculate the second principal minus and so forth, right? Now let's go back to the theorem here. Theorem. So here, now you have some, here, this one have sub k. So now you have this one is not pure H. If you have just H, that is your Hessian matrix. But you have sub K. This one also has sub K. This one also have sub N. That is the not pure Hessian. You take the Hessian at first. When you have sub K, that means that is not pure principal minor. That means leading principal minor. Leading principal minor. Then let's talk about that. Okay. So we have no slide about what is the leading principal minor. Now it's time to think about what is the leading principal minor. Let me talk about this one. Okay. Leading principal minor. So here, when we have a Hessian matrix just like that, this is our Hessian matrix. Okay. What is the leading principal minor? Leading principal minor is that our first one. Okay. So here, our leading principal minor is -8. Just take the first component and that's it. Okay. So it's very simple, right? Okay. And then here, what is the second leading principal minor? So this is just a 2x2 matrix. That's why just take the determinant, and you only have only one element in the second principal minor. That's why second leading principal minor is only one. That's why just take the determinant and that's it, right? So here, your first leading principal minor is negative. Your second leading principal minor is the positive, right? So here, I told you that if this positive, this is non-negative, okay? And then it has the sign as -1 to the k, which means that if the first principal minor is all negative, second principal minor is all positive, then I told you that there is concave function. In the early of this lecture, I told you that in a concave function, that is for the maximization. In a convex function, I told you that is for the minimization, right? So all the principal minors are positive. That is for all the minimization, because that is for the convex. Because that is for the convex. If there is sign is -1 plus -n plus, and that is for the concave, I told you that concave look like the head. That's why that is for the maximization problem. That's why that is for the maximization. That's what I told you in previously, right? So here, let's look at this problem. When you look at this one, the sign is negative and positive. It's interchanging. In the first principal minor, it was negative. In the second principal minor, it was positive. Now you can see that is for the concave. That's why this is for the maximization. So for this saddle point, which makes the 0 for the partial derivation, and you are taking the local maximization in a convex function, concave function. That's why this point guarantees maximum value. That's why to maximize profit, Q1 should be 55/8. Q sub 2 will be 9/2. That's the result of this example. Okay. Okay. So for the Q1, this one, Q2, this one. So Q1 was for customer 1, Q2 was for customer 2. That's why Q1 for the customer 1, Q2 for the customer 2, and that's it. Okay. Let's go to the next example. Okay. So maybe let's do this one. Okay. Find all local maxima, local minima, and saddle point for this one. So when you do this one, you can do more detailed one. Okay. So this is the x sub 1, x sub 2, x sub 1, x sub 2, x sub 1, x sub 2. You have two variables. This is simple calculation, I think, because you have only two variables. The dimension is very low, right? So to find the saddle point here, you have to do the partial derivation with the x1 and x2. That's why you have to do the partial derivation with the x1, then you can get this result. You have to do the partial derivation with the x2, and you have this one, right? Then you make this one as 0, you make this one as 0, right? That's why this one becomes 0, this one becomes 0. Then you combine with the x sub 2, you combine with the x sub 1. That's why x sub 1 combination, x sub 2 is combination. So this can be 0 or this can be 0. This can be 0 or this can be 0. Then let's go to the next slide. So here, so this can be 0 or this can be 0. Okay, or this can be 0 or this can be 0. This can be 0 or this can be 0. That's why you have 1, 2, 3, 4 possible cases, right? So but you have to satisfy this should be 0 and this should be 0. That's why 1 and 3 should be satisfied, 1 and 4 should be satisfied, or 2 and 3 should be satisfied, or 2 and 4 should be satisfied. You have these kinds of 4 different combinations. That's why 1 and 3 should be satisfied, 1 and 4 should be satisfied. 2 and 3 should be satisfied, 2 and 4 should be satisfied. Then, based on the equation, and for the first case, this is only true when your point is 0,0. And 1 and 4 should be true when your point is 1,0. 2 and 3 should be satisfied when your point is this one. You have to calculate by yourself by solving the second order equation based on some simple high school calculation. When you have this equation, then you have to calculate this one and you have to calculate this one for both cases. That's why you have to you have to get this result. Then you have here 1, 2, 3, 4, 5, 6. Now you have 6 stationary points. Now let's evaluate these given 6 stationary points. Now, in order to do the stationary point evaluation, you have to calculate the Hessian at first. That's why, based on this one, you have to calculate the Hessian. That's why do the partial derivation with the x1 2 times, then you have this one. Do the Hessian with the x1 partial derivation x2 first, x1 later, and you have this one. Do the Hessian, do the partial derivation with the x1 at first, x2 later, then you have this one. Do the partial derivation with the x2 2 times, you have this one, right? Then for the 6th stationary point, you apply the first one, 0,0. Then you put 0,0 into here. That's why you have this result. This is your Hessian. Now, you based on this Hessian, you calculate first leading principal minor, second leading principal minor. Based on that, you use the theorem. That's why based on the theorem, this is the saddle point. Okay. So based on this one, I let you know how you can calculate the first leading principal minor, second leading principal minor. That's why you can understand how you can do the you can determine whether this is how you can calculate the first leading principal minor, second leading principal minor. Then you can check whether this point is the local maximum, local minimum, or saddle point. Now you can see this is the saddle point. Okay. For the second one, 1,0, you can put into here. Then 0 and this is not 0. That's why this is the saddle point. Because this is not satisfied this one. This is not satisfied this one. This only holds this one. That's why this only holds the last one. 3.14 theorem. That's why this is the saddle point. Okay. Then let's look at the third one. 1,0. Then when you look at 1,0, then you have this Hessian 0,1. Then you have this Hessian, and then this is larger than 0. This is not 0. Then this is not satisfying theorem 3.12. This is not satisfying 3.13. That's why this satisfies 3.14 0.14, then this is saddle point as well. Okay. Then for the fourth one, you put 0, -1, then you have the Hessian just like that. And then when you find the first leading principal minor, and then you have this result. So this is the notation for the first leading principal minor. Then you have -2, and this is less than 0. And when you have the second leading principal minor, this is -4. This is not 0. So this is also not satisfying theorem 3.412, 3.13. That's why this only satisfies theorem 3.14. That's why this is also saddle point. Now, for this one, fifth point, then you put this result into this Hessian, and then you calculate the first leading principal minor, and then you check that is the positive. When you calculate the second principal minor, then you check that is also positive. Then this is local minimum. And then in a similar way, this is also local maximum. Then you find up to now 4 saddle points, 1 local maximum, 1 local minimum. Okay, you have to do this one by yourself. Then you can solve your midterm exam. Okay. Yes, Itaeho, please let me know your question. You can ask me in Korean, then I can let you know.
네, 감사합니다.
예, 지금 근데 무슨 말인지
그
알겠어요? 저 너무 빠르게 얘기한 것 같아서.
아니요, 저 이해 다 따라가고 있는데 저 헤이시안 저거 미분한 거 -1이 아니고 +1 같아가지고.
어디? 아, 지금 이게 잠깐만. 저도 지금 이거 강의 노트에 오타가 좀 있어요, 있기는. 자,
이거를 그냥
잠깐만.
fx1, x2 마지막 항을 부호 바꾸면은 이제
하긴 그러네.
헤이시안 다 맞으니까.
그러네.
네, 그냥 그렇게
이거 플러스.
이해할게요.
그래서 이거 플러스. 저 이거 example 3.15 이거 숙제 내려고 그래, 숙제로. 이거 학생들이 이거 손을 해봐야 될 것 같아. 이거 내가 말로 설명하면 안 될 것 같아서 숙제로 낼 거거든요. 숙제로 낼 때 한번
네네.
손을 한번 풀어주실 때 그때 한번 수정해서 풀어주면 좋을 것 같습니다.
네, 알겠습니다.
So I just want to make sure. I just let me repeat the question by one Korean student, Itaeho here. He told me that this should be plus. This should be plus. He's correct. We have a typo here. This should be plus. Okay. So when you do the second order derivation here, we only have x of 1, right? When you do the second when you have partial derivation again with the x of 1 again, this should be eliminated. We only have +1. That's why this should be +1, right? 자, 이태호 학생 맞죠? 네, 이렇게 될 거고요.
맞습니다.
네, 이렇게 될 거고요. So we have very intensive class today because I talked a lot here over the video. That's why I would like to resume our class here, and then I would like to give you one assignment today. So let me stop our class here. Maybe up to here. So the method of the steppist ascent and Lagrange multiplier, these are straightforward. So we can finish this one in 50 minutes or 20 minutes. Those are straightforward. So we can explain this one in a fast manner for the next time. That's why let us do this one for the next time, next class after the midterm exam. Next week, not next week, the next week. Not next week, the next week, only first week of the November, we're gonna have the midterm exam, because next week you might be very busy for the grading for the undergraduate classes for your advisors. That's why I would like to have the midterm exam for the 9th week. That's why we will gonna have the midterm exam, not next week, for the next week. So at the time, we will gonna do some exam for this one, and the first chapter we will gonna study about next week, okay? And until the end of next Friday, I will gonna make a link in the Blackboard, and then you have to solve the example 3.15 by yourself, by your hands, line by line. That's the assignment. Because in this lecture, I explained this one just saying the procedure how you can solve, but I truly hope that you have to do by yourself, by your hands. Then you can clearly understand how it works. That's what I want. That's why the assignment is that please prepare your paper and pencil and write down and solve your optimization, and then solve this exercise example 3.15 by your hands, and then scan and upload, make one PDF file and upload in the Blackboard, and that's it until the end of next Friday. That should be the assignment for the end of next week. Okay, then we're gonna have the midterm exam the next Tuesday. Okay, any questions? If not, I will post this video in the YouTube channel, and I will share the link maybe tonight or tomorrow morning. And thank you very much for your time today. And we're gonna meet all together next Tuesday in class. Okay. 자, and let me repeat the midterm exam and examples in Korean here again. 자, 저 한국말로 설명드릴게요. 저 이 다음 주 금요일 자정까지 이 example 3.15를 여러분 연습장에다가 손으로 풀어가지고 스캔하셔가지고 PDF를 하나로 만들어가지고 하나로 만들어 여러분 채점해 보셔서 알죠? 대학원생들이시니까. 그래서 이렇게 그러면 제가 이제 블랙보드로 스크롤 다운하면서 여러분 푼 거 다 볼 수 있거든요. 압축하시면 다운받아서 압축 풀어서 하나씩 보기 너무 힘드니까 여러분도 채점해보셔서 아시죠? 너무 힘들거든요. 그러니까 이렇게 쭉 스크롤 다운해서 볼 수 있게 만들어서 PDF를 하나 만들어서 올려주시면 되겠습니다. 다음 주 금요일까지 이걸 손으로 한번 해보셔야 돼요. 그래야 이걸 여러분께서 옵티마이제이션을 제대로 이해할 수 있으니까 해보시기 원하고요. 그 다음 주 원래 다음 주 목요일 이거 원래 두 개 남았는데 이거 금방 끝나거든요. 금방 끝나는데 이번 수업은 제가 영어로만 해가지고 왜냐면 이거 비디오로 녹화하면 기록이 남으니까 한국말로 섞기가 좀 약간 부담스럽네요. 그렇죠? 영어로만 해가지고 지도를 빠바바박 나가가지고 여기까지 하기가 좀 약간 저도 좀 벅차가지고 이 부분은 제가 다음 시간에 이거 10분이면 끝납니다. 이거 별로 어렵지도 않아요. 10분이면 끝나니까 이거는 다음 수업 시간에 리아프노프 챕터 1 나갈 때 시작할 때 잠깐 나가고 시작하겠습니다. 그렇게 하면 될 것 같으니까 이거 다음 시간에 시작할 때 하고요. 여기까지가 여기 10분 하니까 여기서 끊어도 괜찮을 것 같습니다. 그렇고요. 그 다음에 다음 주 금요일까지 여러분이 example 3.15를 숙제로 내시면 그 다음 주 화요일 날 저희가 중간고사를 보도록 하겠습니다. 알겠죠? 예, 질문 있으실까요? Any questions up to now? No? If not, this is the end of class today. Okay? Thank you very much today, and I will post this video tonight or tomorrow morning in our YouTube channel, and I'm gonna share the link with you at the time. Okay? Thank you, and have a good day. Bye bye. Thanks. Bye bye. 감사합니다. 네. 근데 이태호 학생? 예, 지도 교수님
네,
누구세요? 지도 교수님.
저 석준희 교수님이요.
아, 그렇군요. 예, 알겠습니다. 감사합니다. 고생하셨어요.
수고하셨습니다.
네.